Hello everyone, welcome to Deeksha Karnataka. Just let me check if my streaming is working, then I will start the class. Just let me check once. Yeah, it's working. Today is the last part of our chapter electric charges and field. So we have started electric charges and field. We have already discussed two parts. So if you have missed the two parts, you have to check them out. And in today's part, we will basically the thumbnail. Ignore the thumbnail. Thumbnail is wrong. Okay. So we will be discussing. Just let me check if it is yeah. The PPT is correct. The thumbnail is wrong. So today we will be discussing the last part, electric flux, where we will be discussing charge distribution, Gauss's law, and application of Gauss's law. So we will start with electric flux, then we will see three different types of charge distribution, which is very important, and then we will move on to Gauss's law, the most important concept if you are preparing for KCET exam every year. From this concept and application part, 2 to 3 question comes from this concept, Gauss's law alone. If you take last 3-4 years, every year you will see questions directly coming from Gauss's law. Okay, we will solve some of the questions. And our next class will be PYQs, 25 PYQs from this chapter from KCET. So do not miss that session as well. So let's start with the first concept, which is electric flux. So what is the meaning of flux? We will understand the concept of flux. Sushant Chinta, teach properly. Yes, we are teaching properly only. If you have any questions, please ask. Right? I think you are new to our channel. Because we are teaching properly, we have already completed 2 chapters, and if you have any doubts, any questions, mention that in the chat. Right, Shushanta? So let's start. So electric flux, before moving on to electric flux, let us understand what is the meaning of flux. So flux means basically flow. Okay, and the term flux comes from the flow, and it is basically for fluid. When the fluid is flowing through a say a pipe. Okay, some fluid is flowing through this pipe. Okay, and you are trying to measure the flux which is coming out. So how to calculate that? So a liquid flowing with velocity v through a small flat surface. So this is the small flat surface. Okay, in a direction normal to the surface. So the direction of the fluid flow is normal to the surface. So this direction is normal to the surface. Okay, the rate of flow of liquid is given by the volume crossing the area per unit time, VDS, and represents the flux of liquid flowing across the plane. So liquid flowing across the plane is basically the volume of fluid flowing through the surface area in 1 unit time is called the liquid flux. Here we are talking about liquid flux. We will move on to fluid flux soon. Okay, so liquid flux is basically represented by the amount of fluid flowing through unit surface area per unit time. That is the definition of flux. Now electric field is something which is static. It is not flowing. Okay, even though we represent it using arrows, electric flux is not flowing. Okay, so we have to basically it's an analogous quantity. Analogous quantity means for example, we say that some city is for example, Ahmedabad city is called Manchester of India. So is it Manchester? It is not Manchester, but it is called Manchester of India. So it is an analogous quantity. Analogous means so same concept of fluid we will apply to electric field, and we will call it electric flux. Okay, so let us understand that for detail. For the case of electric field, we define an analogous quantity. and call it electric flux. Why it is analogous, it is not equal? Because electric field is not flowing. You have to understand that electric field is only represented by lines. It is actually static, it is not flowing. Okay, we should however note that there is no flow of a physical observable quantity. Unlike in the case of liquid flow, electric flux is a scalar quantity and its SI unit is Newton meter square per coulomb. Okay, so this unit is also very important to remember. Now what is electric flux? So suppose the electric field, if the electric field is normal, to the surface, then simply you take a small surface area, say delta S, and you take the electric field through that surface area, you multiply, you get the electric flux. Delta phi equals to E delta S. But what if the electric field is not normal? So electric field can pass through a surface right 90 degree, or it can pass through at some other angle as well. For example, here we have taken where the surface area is kept like this and electric field is passing like this. So in that case, the normal to the surface is making an angle theta with the electric field. The normal to the surface is making an angle theta with the electric field. So in that case, flux can be written as E delta S cos theta. Same thing, everything is same. Small surface area, you are considering small surface area ds. Only thing is the electric field is not normal. Normal means 90 degree, not 90 degree. Okay, normal, do not think it is normal, abnormal, not those kind of normal. In physics, we use the term normal for representing an angle 90 degree. So if the angle is not 90 degree, if it is at certain angle theta, then electric flux becomes E delta S cos theta. The electric flux becomes E delta S cos theta. And we know that surface area is a vector quantity, electric field is also a vector quantity. So when two vector quantities are multiplied and the resultant is a cos product, resultant is a scalar product, then definitely it will be a dot product. Okay, so it can be represented as E dot delta S. It can be represented as E dot delta S. So this cos theta is basically absorbed by this dot product. We know that in our P1 we learned that if A dot B is there, this can be written as AB cos theta. Right, cos means this dot product. Right, so here also cos theta is there. So from cos theta we are moving on to dot product. I don't read your comment. Where is Ankit Sir? Ankit Sir, you can discuss. It is not a maths class. During the maths class you can ask. Okay, now let us move on to a question. Okay, a charged particle small q is placed at the center of center O. A charged particle q is placed at the center O of a cube of length L. So the cube is of the length L and a charged particle small q is placed at the center. Okay, another same charge small q is placed at a distance L from O along the line parallel to AB as shown in the figure. So here this charge is O, Q, this charge is Q, and this distance is L. The distance is given here as L. From O along the line joining to AB as shown in the figure. Then the electric flux through the face BGCF. So what is the electric flux through this surface? Now you might feel that, sir, this might looks like a Gauss's theorem based question, and Gauss's theorem is not yet taught in this class. We will teach that, but how to solve it? Don't worry, this is not a Gauss's theorem based question. This is a very simple electric flux related question. So we know that electric flux is what? Electric flux is basically E dot ds or E dot s. If you know the surface area is easy to calculate and it is normal. So E into S, if you calculate electric field, if you calculate surface area, you will get the required electric flux. You don't need to apply Gauss's law here. So but how to calculate electric field? So both charges are positive here. Both charges are positive. So this positive charge will have an electric field in this direction. This charge is also positive. It will have an electric field in this direction. So both electric fields, they will be equal and opposite. Why they will be equal? Because this total length is L and this is the center. So this distance must be L by 2. And this total length is also L. So this distance should be also L by 2. Right, this distance should be also L by 2. So both distances are L by 2. Now we know that electric field is given by E is equal to K Q by R square. So here R square is same. Their directions are opposite. So magnitude wise they are same. Direction wise they are opposite. That means their net electric field will be E minus E. One is positive. If you take this side as positive, this will be negative. So E minus E. So net electric field will be 0. So net electric field 0 means the net flux will also be 0. Okay. So the answer to this question will be 0. So do not always think that if it is a diagram based question, students think that it is a difficult question, hard to solve question, but actually if you go into the little detail about the question, you will feel that this is an easy question. This is not a difficult question and you do not need to apply Gauss's law over here. Okay, this is simple, basically simple electric flux concept question. Now before going to Gauss's law, we need to learn about 3 different types of charge distribution. First is line charge distribution. What is the meaning of line charge distribution? You have a single solitary line and you have added some charge on this line. It can be positive charge, it can be negative charge. Basically it's like an electric wire, but it is not conducting electricity, it is only having some charges distributed over this line. Okay, this is called line charge distribution. Okay, and correspondingly we need to know about line charge density, which is represented by the symbol lambda. Line charge density is represented by the symbol lambda. Okay, now what is lambda? Lambda is defined as total charge on the wire divided by total length of the wire. Very simple definition, very simple formula as well. So if you know the total length, if you know the total charge, you can calculate lambda. But sometimes it is difficult for us to measure entire length, measure entire charge. So what we will do, we will take a small portion of the wire, we measure how much charge is there, and we will say that the lambda is actually given by delta Q by delta L. Delta Q is the small charge located in this small length, which is called delta Q. Okay, and the length is delta L. Then delta Q by delta L is called line charge density. Okay, and its unit is coulomb per meter. This unit is very important for PU exam. This is a very common MCQ question which comes year after year in your maybe in your FA1 or midterm. Okay, maybe in your final exam also. Line charge density is coulomb per meter, that is the unit. Now let's move on to the second quantity, which is surface charge density. Okay, surface charge density, same as line charge, it is basically a surface. Okay, instead of simple line, it is a surface, two-dimensional surface. Okay, it can be a page of a paper, it can be a metal sheet. Okay, if you add some charge on that paper, then you can consider it is a charged surface. Previously it was charged line, it is a charged surface. Similar to that of line charge, you can calculate the surface charge density, which is denoted by the symbol sigma. This concept is very important, not only in this chapter but in the next chapter, in electrostatic potential and capacitance chapter also, this surface charge density will come into play. So what is the formula? Very simple, as same as the line charge density, total charge divided by area. Okay, so in that case it was only length, so it was charge by length. Here it is area, so charge divided by area gives you surface charge density, and in terms of small area and small charge, it is delta Q by delta A. So you take a small area, you measure how much charge is there, you call that charge delta Q, you call that surface area delta S, then delta Q by delta S. Actually they have used S in your textbook, I am using A, so don't get confused. I am using delta A. Okay, that is easier. So delta Q by delta A gives you the surface charge density. And last but not the least is volume charge density, rho. Okay, now first we started with one dimension, that is line. Line is one dimension, surface area is a two dimension, and last is a volume, which is a three dimension. Okay, so it is 1D, it is 2D, and it is 3D. And what is the unit of surface charge density? Unit of surface charge density is coulomb per meter square. Okay. Now volume charge density is exactly same as line charge and surface charge. Only thing, it's a three dimension, so you have to consider the volume instead of surface. Okay. So what is the volume charge density? It is same as total charge divided by volume. And if you take a small volume, surface charge density becomes Q upon delta, delta Q upon delta V. Its unit is coulomb per meter cube. All surface charge densities and their respective units, all of them are super important. Give me a moment. Okay, now let's move on with our main topic, which is Gauss's law. So Gauss's law is the most important, very simple law. It is important for your PU exam, it is important for your KCET exam, it is important for all exams. But on the surface it might look very simple and very easy. So statement, what is Gauss's law statement? So basically Gauss's law measures electric flux. It measures electric flux through a closed surface. Okay, so electric flux through a closed surface S is given by phi equals to Q by epsilon naught. Okay, where Q is the total charge enclosed by the surface. So if Q is the total charge enclosed by a closed surface, remember it's a closed surface. What is the example of closed surface? Example of closed surface is a football. Okay, football, if you stay inside a football, then it is a closed surface. Okay, if you are staying inside a room, the outside of the room is closed surface. If you are in a room with all the doors, windows, etc. are closed, then you can consider from outside, that can be considered as a closed surface. What is an open surface? Same room, if you open the doors, open the windows, then it is an open surface. Okay, you cannot apply Gauss's law for open surfaces. Good evening, Pradeep. Yes, hi. Sorry, I saw your comment a little late. How are you? So, you have to remember that Gauss's theorem is applicable only for closed surface, not for open surface. Very, 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 very important point. Okay. And from the previous part, from the flux part, we know that small flux can be written as E into delta S. Okay, we have studied that if the electric field is at some angle, then the angle is theta. Electric field, suppose this is electric field, this is surface area. Okay, then electric flux is given by E dot ds. Or delta S. Now if you want to calculate the total electric flux through this surface, then total flux is basically integration of E dot ds. ds is basically the integral. Okay, if you have studied integration, it is okay. If you have not studied integration, then you will learn through time. I have done a class on bridge course where I have discussed about basic integration. You can check that out. This symbol is very special, which is called close integration. Close integration means your starting point and your ending point both are same. So if you start somewhere and you go in a loop, you come back to the same point, then it is called closed integration, right? So closed integration basically means starting point and ending point both are same. Okay, so and for line you can imagine it's like a circle. Okay, for a line you can imagine it's like a circle. For surface you can imagine it's like a sphere. Okay, so basically it's sphere. When you start somewhere, you go each and every possible points and then you come back to the starting point again. So that is called a closed surface, and this kind of integration is called closed integration. Okay, so closed integration has their benefits. Some cases it can be 0, some cases it will be the surface area. Okay, now let's move on with some of the very important points about Gauss's law. Gauss's law is true for any closed surface, no matter what is the shape or size. So there will be some question that might come in your PU exam, that Gauss's law is only valid for symmetrical surface, Gauss's law is only valid for spherical surface or cylindrical surface. Remember, Gauss's law is valid for all types of surface, not only any symmetric surface. Here Q includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. So suppose you have a surface area, charge can be located anywhere. Okay, it does not need to be present at the center. It can be located anywhere inside the surface. The formula that we mentioned, Q by epsilon naught, phi is equal to, here this Q is actually sum of all the charges. Okay, if any charge is located outside, that charge we will not consider. Any charge located outside, that charge we will not consider. The surface that we choose for the application of Gauss's law is called Gaussian surface. Gauss's law is often useful to calculate the electric field for symmetric surface. So this is useful. This is useful, but this is not mandatory. This is useful to calculate the electric field for symmetric system, but it is not mandatory to use only symmetric systems. Okay, so this is very important point to remember, especially for board level MCQ questions. Okay, now let's move on to the next part with a question. A cubical Gaussian surface has side of length A equals to 10 centimeter. Electric field lines are parallel to x-axis as shown. The magnitude of electric fields through surfaces ABCD and EFGH are 6 kilonewton per coulomb and 9 kilonewton per coulomb respectively. Then the total charge enclosed by the cube is, take epsilon naught equals to 9 into 10 to the power of minus 12. So here if you see the diagram carefully, basically here we have a surface, a cube. Okay, so some electric field is coming in from this surface, some electric field is going out through this surface. Okay, it is mentioned that the electric field near this surface is 6 kilonewton per coulomb and here it is 9 kilonewton per coulomb. Okay, so this is 6 kilonewton per coulomb, this is 9 kilonewton per coulomb. So what is the charge enclosed inside the surface? If these two are equal, if incoming and outgoing flux are equal, then answer would have been 0. But because they are unequal, it will not be 0. So, and you also have to find the sign of the charges. So first task is to find the electric fluxes for individual surfaces. So what is the electric flux, incoming flux through ABCD? Okay, so for ABCD, what is the incoming flux? Say phi in, which will be given by electric field into surface area. Because it is normal, so we do not need to add any cos theta over here. Okay, so you are already answered is B. Okay, let's see whether you are correct or not. So electric field is E. Okay, and because they are normal E and A, you do not need to add any cos theta over here. So what is the value of electric field? Value of electric field, incoming electric field is 6 kilonewton. Kilo means 10 to the power of 3. Kilo means 10 to the power of 3. Into surface area. What is the surface area? Surface area is very simple. It's a square surface. So you have to just need to multiply the length and breadth. Both are same. Okay, so here it is given as 10 centimeter side is 10 centimeter. Okay, so it will be 10 into 10, but remember both of them are in centimeters. You have to convert them into meters, so you better write them as 10 into 10 to the power of minus 2 into 10 into 10 to the power of minus 2. So make this a habit. Whenever you are converting centimeter to meter, always add 10 to the power of minus 2. That reduces complications, that reduces any errors if you are doing decimal point based calculations. Okay, you are not allowed any calculator in the KCET exam, so you have to build the habit of using 10 to the power of minus 2 from centimeter to meter. Okay, similarly when you are converting from meter to centimeter, which will be very less, you have to divide by 10 to the power of we have to multiply with 10 to the power of plus 2. So now let us simplify. You will get this 10 into 10 is 100, 100 and 10 to the power of minus 2 cancels. You get 60 Newton meter square per coulomb. Okay, so this is the incoming flux. Similarly, outgoing flux, so this was E1, say this is E1. Okay, this is say E2. So this was E1, this is E2. Okay, so E2 is outgoing flux. So outgoing flux will be E2 into area. Area will remain same. And if you just change the 6 with 9, you will get the outgoing flux, which will be 90 Newton meter square per coulomb. You don't need to do any calculation. This is the smart technology, smart trick that you have to apply. As soon as you have solved for 1, you remember this was 6 kilonewton, I got 60. This was 9 kilonewton, surface area is same. So I must get 90 Newton meter square per coulomb. So the net flux is calculated. So incoming and outgoing flux is calculated. Now we have to calculate the net flux. What is the net flux? Net flux is very simple, bigger minus smaller. Bigger minus smaller. Which is bigger here? Out is bigger, in is smaller. So we will basically do out minus in, which is 90 minus 60, that is 30 Newton meter square per coulomb. Okay, so net electric flux is what? It is outgoing. Net electric flux is outgoing, right? It is basically outgoing. Why outgoing? Because outgoing flux is more than incoming flux. Now when you get outgoing flux more, is it for a positive charge or for a negative charge? If you remember, positive charges, they have electric field lines outward. That means if net flux is positive, outgoing flux is positive, that means the charge inside must be a positive charge. So whatever is inside here, it is a positive charge. Whatever inside here must be a positive charge. It cannot be a negative charge. If the net flux is negative, that is outgoing flux is negative, or total flux incoming is positive, then you can say this is a negative charge. Remember, this is very carefully. If net outgoing flux is positive, the charge is positive. If the net outgoing flux is negative, then the charge is negative. So here net outgoing flux is positive, that means the charge is a positive charge. So option B will not be a possible. So if you have answered option B, this is not correct. Okay. Now let's see. So net flux is 30 Newton meters per coulomb. Now we have to calculate our Gauss's law, that is net flux is basically Q upon epsilon naught. So Q is basically epsilon naught into phi net. Now Q epsilon naught value is 9 into 10 to the power of minus 12 given in the question, and we have calculated net electric flux is 30. So it will be 270 into 10 to the power of minus 12 or 0.27 nano coulomb. Okay, if you adjust 3 decimals, 10 to the power of minus 9 will be adjusted and you will get 0.27 nanocoulomb. So option C is correct, not option B. Okay, not option B, neither option D. Okay, Sushant and Shuvarna. Okay, so both options are not correct, neither B nor D, because first of all you have to understand the net flux here is positive. Net flux positive, we mean that if the net flux going out, that is positive, that means the charge inside has to be positive. Okay, if the charge is negative, what it does, it takes electric field lines. Okay, all the electric field lines come inward. So if the net flux coming inside is positive, then we say the charge is negative. But here net flux going out is positive, that's why the charge is positive. Very, very careful. Or you can just remember, we only need to calculate outgoing flux, which is much easier. Going forward, that you need to remember that if net outgoing flux is positive, charge is positive. If net outgoing flux is negative, the charge is negative. That is very simple, one single thumb rule, that we have to calculate out minus in. Okay, you have to calculate out minus in. Is it positive or negative? If it is positive, means charge is positive. If it is negative, means charge is negative. That is one very simple thumb rule that you can follow. Okay, now here are the applications of Gauss's law. First we will do it for a straight line. Okay, this theory came in 2026 final exam. Okay, I predicted that this will come this year in the morning of the exam, and this came in the exam itself. Okay, but I don't think that this will come, this derivation will come again, repeat again in the final exam, but this derivation is important for your FA1, for your midterm, etc. Okay, but this derivation may not come in the final exam, which is less likely. I will not ignore it, but yes, you have to study it anyway for FA1 and midterm exams, but it may not come in the final exam. So this is a straight line, infinitely long straight line, and you have to find electric field due to this straight line at some distance r from the straight line at a point P. Okay, so this is the basic problem. So how to solve this problem? For that you have to construct, for whenever you are given a charged surface and they are asking you to calculate electric field, okay, you have to apply Gauss's theorem. Okay, there is only one way to solve, apply Gauss's theorem, and as we have studied that Gauss's theorem is applicable, easier to apply for which surfaces? Symmetrical surfaces. Okay, for a straight line, the symmetric surface is a cylinder. For a straight line, the symmetric surface is a cylinder. So basically we have to construct a cylindrical Gaussian surface. This dotted line actually represents an imaginary Gaussian surface. Okay, the length of this Gaussian surface we have taken as small l, which is again based on our imagination. It can be small l, it can be capital L, does not matter, eventually it will be simplified. Okay, electric field is given by E. So how can we calculate this electric field? We have to start with our Gauss's theorem, that is phi is equal to charge enclosed by epsilon naught, and that is given by integration E dot ds. Okay, so here if you see that ds is this surface, the curved surface is ds. Okay, this top surface and bottom surface are excluded because electric field is perpendicular to that. That means the electric flux will be 0 through them. Okay, so if you consider ds here and electric field here, so that means they are 90 degrees. So E dot ds will be 0. So you do not need to calculate anything for this bottom and top surface. Only the curved surface is required. Don't need to think too much, only you need to consider the curved surface, that's sufficient. Okay, so electric field is basically E dot ds. How to calculate? We will say that because the surface is symmetric, electric field is independent of where you are applying this formula. It can be this point, it can be this point, it can be this point. So on the surface of this cylinder, electric field is constant. On the surface of this cylinder, any point, electric field is constant. So anything is constant. In differentiation, what happens? Constant comes out of the differentiation. Same thing happens in integration as well. So E will come out of the integration, and because it's a constant, we can write it will be simply E ds. Okay, dot product will is 1, cos theta is 1 here, so E dot ds basically E into ds. Okay, and that is equals to Q enclosed by epsilon naught. Now what is this ds? ds basically the surface area of this curved surface. ds is basically surface area of this curved surface. So you can write this as E into 2 pi RL. 2 pi RL is the surface area of a curved cylinder. So that is Q enclosed by epsilon naught, or you can write this as E equals to 1 by 2 pi epsilon naught Q enclosed by L by R. Okay, now Q enclosed by L is basically, if you take this length and if you take the charge inside that, that gives you the line charge density. That gives you the line charge density. So electric field is 1 by 2 pi epsilon naught lambda upon R. Now to write it in a little fancier way, we can write it as E is equal to 1 by 4 pi epsilon naught, because this is the Coulomb's constant, 2 lambda by R. Okay, so this is the fancier way to write it. You can remember this formula or this formula, both formulas is okay. And based on this formula also, we have seen questions, numerical questions do come based on this formula. And one more important part is that electric field is inversely proportional to the distance. Electric field is inversely proportional to the distance. Normally what we have seen, if the point charge is there, for a point charge electric field is inversely proportional to 1 by r square, right? But for a line charge, if the charge is line, the electric field is not proportional to 1 by r square, it is inversely proportional to 1 upon r only. This is also a point of MCQ objective question. Okay, so if you solve your question bank which is published last year, you will see this kind of questions are there in your question bank as well. Now next, this one, the derivation is not required. Electric field due to an uniformly charged infinite plane conducting sheet. So this is a plane conducting sheet. For example, consider this display board, okay, where I am writing, smart board. So this can be considered to be a surface. Now if you extend this surface long enough on both sides, okay, then it can be considered to be a infinite plane sheet. Now in practical cases, we do not see long, very long infinite sheet. Obviously infinite is not possible, but if the distance of the point where we are measuring the electric field is small compared to the dimension, compared to the size of the sheet, then we can still apply this same formula that we are going to that is there for this surface. Okay, so if the distance is small compared to the dimension, that means the distance is small compared to the dimension of the surface, that point can still be considered as a charged surface infinite sheet. So for example, we have a say 50 centimeter by 50 centimeter square sheet, and the distance where we are measuring the electric field, say 1 centimeter. So 1 centimeter is 1 by 50th time smaller than that of the dimension. That means we can still apply the formula. Now very interesting fact is that electric field due to a large infinite sheet, okay, large sheet of paper, electric field is constant near the sheet. Electric field is constant near the sheet, which is given by sigma by 2 epsilon naught. Sigma by 2 epsilon naught, sigma is the surface charge density. So as you can see, electric field is constant. It does not change with distance. Okay, that's why it is very, very important. If the dimension of the distance where we are measuring, if the distance is smaller compared to the dimension of the sheet, we can still apply this constant electric field formula, and that formula is equally valid. Okay, so remember that electric field is constant near a large charged sheet. Okay, sheet means paper. Okay, sheet means paper. So very large paper which is charged, okay, electric field will be constant near the charged sheet. Okay, so this derivation is not there, but sigma by 2 epsilon naught, you will have to use it in the next chapter. Remember this formula. This formula is important. Now the last application of Gauss's law, which is field due to an uniformly charged thin spherical shell. Okay, shell means what? Shell means you can consider it's like a covering. Okay, for example, if you are someone who eats egg, or if you have seen someone eating egg, so once the egg is broken and once the everything inside of the egg is coming out, then the covering of the egg is called egg shell. Shell means the covering, which is covering the egg inside. So shell means it's like hollow inside, okay, but it has a solid surface outside. Okay, so it has a thickness, it have a very small thickness, and inside part is hollow. Now whatever we are applying here, the same theory, same concept can be applied for a conducting sphere. Remember, charge thin spherical shell or conducting solid sphere as well. The reason we will explain in next chapter. Okay, but the theory that we are using here, you can use the same theory for a conducting solid sphere as well. So if you see conducting solid sphere, whatever formulas, calculations that we have derived in this chapter, the same formula can be used for a conducting solid sphere as well. So don't get confused with shell and sphere. You might say, sir, you have taught shell only, why we have to solve for a conducting sphere, but how to solve it? Don't worry, conducting solid sphere and shell both have same equation. Okay, so equation wise they are same. Now when you charge this shell, obviously because it's a shell, all the charges will stay on the surface, right, within this zone only. All the charges are in this zone only. Now how to find the electric field? So because the shape is spherical, the Gaussian surface that we have to consider will also be spherical. Now when you are doing the derivation, suppose this derivation came in your exam, the diagram for any such derivation, the diagram is compulsory. Without diagram, you will not be awarded any marks. Okay, so this is the spherical shell. You can use compass, obviously. Compass, draw a circle. From the same center, draw another bigger circle. From the same center, you draw another bigger circle, but the last final bigger circle, you draw it in a dotted line, so that it represents the Gaussian surface. Now you mention in the question answer sheet that let us consider a thin spherical shell and a Gaussian surface such as P. We are trying to find the electric field due to a point outside the shell, which is located at a distance r. So r is greater than the radius of the shell. It is not too much greater, just outside you can apply this theory. Now how to do that? Again, our Gauss's theorem, which states that E dot ds equals to Q enclosed by epsilon naught. Okay, so it is basically Q enclosed by epsilon naught, that is Gauss's theorem. So suppose the charge, total charge on this surface is capital Q. Total charge on this surface, say capital Q. Okay. Now if you consider this as your Gaussian surface, this dotted line, okay, so what is the total charge enclosed? Total charge enclosed will definitely be capital Q only here, because entirety of this charge is enclosed by this Gaussian surface, right? And because it's a spherical symmetry, electric field will be constant no matter where you are calculating the electric field. Okay, so it will be constant everywhere on this spherical Gaussian surface. Okay, concentric. This sphere is concentric, obviously same center as the shell, right? So electric field will be constant throughout this surface. So that's why we always choose symmetrical surface whenever we apply Gauss's theorem. Okay, now what is the charge enclosed? That is Q. Now electric field, as I said, it is constant, it will come out of the integration, and electric field and the surface are perpendicular, so that means cos theta is 1, so you will get E ds Q by epsilon naught. Okay, now what is ds? As I mentioned, basically ds is the, when you are doing close integration ds, it gives you the total surface area. Total surface area. What is the total surface area in this case? Total surface area will be that of a sphere. What is the surface area of a sphere? It will be 4 pi r square. Surface area of this bigger sphere of radius r. Okay, surface area of a sphere is 4 pi r square. Here the radius of this larger Gaussian surface is small r. This capital R is immaterial. Only thing you need to check whether this is greater than or less than. Whether it is greater than or less than, otherwise the r is not important. So E into 4 pi r square equals to Q upon epsilon naught. Now what is, now let's simplify. You will get 1 by 4 pi epsilon naught Q upon r square. So this is the electric field due to a charged spherical shell. Now this formula is very same as a point charge. This formula is very same as the point charge. Only thing is, if you assume the entire charge is located at the center of this shell, then this is the formula for electric field. Okay, so basically you can assume entire charge is located at the center of the electric field. Okay, center of the electric shell. Now one important part is, even though you can do that, this is only valid for points which are outside the shell. Okay, this formula or concept is not applicable for points inside the shell. We will see that. And one more formula which comes from this fact, that if the surface charge density is given sigma, then this capital Q can be written as 4 pi capital R square into sigma. Okay, charge density is charge divided by surface area. So surface area is 4 pi r square. So if you multiply surface area with charge density, you get the total charge. Total charge for a surface is always surface area into charge density. Sometimes we use this formula as well. Okay, it came once. If you use this formula, the problem could have been solved a little easier. Okay, 4 pi epsilon naught. Here it becomes 4 pi r square sigma divided by small r square. So 4 pi cancels. You get r square sigma by small r square epsilon naught. Okay, so this is a formula which is electric field due to a spherical shell in terms of surface charge density. Okay, now let's move on. Field due to an uniformly charged spherical shell inside the shell. Now let us consider the case where the distance is less than the radius. Distance is less than the radius. So if the distance is less than the radius, entire charge is located here, and this is your imaginary Gaussian surface. How much charge is located there? The entire charge is located outside the shell. That means charge inside here, Q enclosed, is actually 0. Okay, because this Gaussian surface is smaller than the shell, so entire charge is located outside, and Gauss's law only considers the charge which is located inside this. So because this is your Gaussian surface, okay, there is no charge inside this. That means electric field inside will be 0. For a spherical shell or a conductor, electric field inside will be 0. Hello Iconic, yes, I know, I identified you. Okay, today is CET result, SSS is saying. As of now there is no such information. We have checked the CET website in the morning. That is our job. Every day we come check the website, we open it, we see if something new is there. They have updated their interface a little, but we have not seen any notification regarding the CET results. But if it is published, definitely we will update you. Okay, there are some new rumors going on. It should be coming out soon enough. Obviously, as you know, there was a retest happened for agricultural students, which I think happened yesterday. Okay, and after that only they will calculate all the marks, they will tabulate all the marks. They are ready, only they are waiting for the final tabulated marks for the practical exam that was held yesterday, and then they will publish it. Maybe not today, but maybe tomorrow they will publish it. Okay, I believe it will be too early to publish unless they have already tabulated everything, they are ready on everything. Okay, maybe tomorrow you can expect the result. Field due to an uniformly charged thin spherical shell. If you plot the graph of electric field versus radius, the electric field from E to R is basically 0. So when the point is inside the shell, electric field is 0. Up to where? Up to the radius. Up to the radius, electric field is 0. Okay, and as soon as electric field you go out of the shell, starting from the surface, electric field decreases with 1 upon r square. So inside it is 0, suddenly it goes up to a value at the surface, and from there onwards it decreases 1 by r square. This graph pattern, remember it, identify it, memorize it in your brain, because this is one of the most common pattern in KCET, and many times this question was asked in KCET. Okay, so this is one of the most common question. You got 92.5. Yes, Iconic, I remembered you. Now, one question. To equal and opposite charges of mass m1 and m2 are accelerated in uniform electric field through the same distance. What is the ratio of their acceleration a1 by a2 if the ratio of their masses is m1 by m2 is equal to 0.5? This is a general question, not related to Gauss's law directly. This is basically based on electric field. Okay, two equal and opposite charges of masses m1 and m2 are accelerated in uniform electric field through the same distance. Now, so this is an electric field based question. This is like a chapter summary. This is not only Gauss's law. This is kind of a chapter summary question. Okay, so how do I approach this kind of question? So if you see that mass is given, charge is given, okay, and they are asking you the ratio of their accelerations, mass ratio is given. So don't worry, okay, charges are equal, charges are opposite, that does not matter about the acceleration eventually. Okay, so you only need to remember that force acting on a charge is given by Q into E. So force acting on a charge, they does not differentiate between positive and negative charge. Yes, direction will be maybe opposite, but force, magnitude of the force will be same. Okay, so from here you can calculate the acceleration, which is basically father equals to ma. Father equals to mass. So force equals to m1 a1. So a1 equals to q into e by m1. Similarly, a2 will be q into e by m2. One will be positive, one will be negative, but magnitude wise the sign will be same. So basically, what is the ratio of a1 by a2? Both charges are equal and electric field is constant. So QE, force will be same, right? So a1 by a2 will be equals to basically QE by m1 into m2 by q into e. So q into e cancels, you get m2 by m1. Now if you see m1 by m2 is given 0.5, so m2 by m1 will be 1 by 0.5, that is 2. Okay, so it will be 2. So correct answer for this question is 2. Easy question, right? So this is basically like a fool question where they are trying to fool you. Question is easy, answer is easy, but if you don't pay attention, you will lose marks. Okay, so you have to practice these kind of questions. Now let's give you the daily practice questions. Last time I have not received a comment on daily practice questions, so do check this out. And obviously the PDFs will be available on our WhatsApp channel. So if you have not joined our WhatsApp channel, the link of the WhatsApp channel is given in the description section of this video. Do join there, and obviously share this video with your friends as well, and whenever there is an update, whenever we are doing something new, it will be published in our WhatsApp channel. We are not giving you the file yet because the chapter has to be completed, and also some KCET related updates are going on. So if you are joining late, we may not get the link. So we will share, once the chapter is completely done, we will share entire chapter PDFs to you so that you can revise it later on. Okay, so daily practice question, but you can pause the video anytime. You can come back to this video, pause it, see the question, solve it, and mention the question answer in the chat. Not now, you are in a hurry, take time, solve it properly, mention in the comment below. An infinitely long thin straight wire has uniform charge density, that is lambda is given. What is the magnitude of electric field at a distance 20 centimeter from the axis of the wire? Easy question, simple formula you use and you will get the value. The next question, however, is slightly tricky. This question is tricky. An infinite number of point charges, infinite, not 1, 2 or 3, it is an infinite number of point charges, each equal to Q, are placed along the x-axis at x equals to 1, x equals to 2, x equals to 4, x equals to 8, and so on. So 1, 2, 4, 8. So if you see, basically it's in GP series. 1 multiplied by 2, 2, 2, 2, 2 to the 4, 4 to the 8, 8 to the 16, like that. So it's a GP series, and common factor is 2. If the resultant electric field at the origin due to all these charges is 360 volt per meter or Newton per coulomb, then what is the value of Q? So basically it says that you have some charges. I am giving you some hint. This is slightly tricky question. So x equals to 1, x equals to 2, x equals to 4, x equals to 8, etc. Okay, so this is how to approach this question. You have to find the electric field for this E1, which will be kq1 by r square. Charges are same, okay, but distances are same. So kq by r square, r1 square, kq by r2 square. So you add all these electric fields at the center, at the origin, and then you find the total electric field by sum of all these electric fields. So you solve it. Once you write down the equations, it will be easier for you to solve it, and you will get an infinite GP series. I hope you have solved questions based on infinite GP series. Once you get the series, it will be very easy for you to solve. Okay, and obviously the two things that I always remember you, that you have to join our WhatsApp channel, and if you are share this video with your friends and like this video. Okay, Suvarna and anyone else answering, I will take the answer only in the main comment of this video. Okay, please wait, the video will be over. Once the video is over, you will be able to comment in the main comment section. So do comment in the main comment section only. That's how I can check your comment anytime. Okay, so yes, so the live is over. I will see you in my next class. Till then, bye. The next class will be again scheduled very soon. So do follow our channel as well if you have not followed, and like this video. I'll be back. Till then, bye.